So let's go through this. If you've got questions about the grading of your homework, please come talk with me about that after the class is over. Okay, so this is the first question. This is set up around the data that you used for exercise 4, and you're asked essentially to compute the dimensions of this box around the digital elevation model data in terms of lengths and also of areas. So this is my solution. What I did first was to calculate the lengths of the long sides, which are AD and BC, and that's just the radius times the change in latitude converted to radians, and it comes to 222.4 kilometres. I posted this solution on the class website so you can check it out yourself later if you want to. Then as you go across for AB and CD, you've got RE cosine of phi times delta lambda. In this case the delta lambda is just 1 degree, which is 0.01745 radians, and the cosine of phi depends on whether you're at 43 degrees at the top or 41 degrees at the bottom. And at the top it's 43 degrees and it comes out to 81.32 kilometres, and at the bottom it's 41 degrees and it comes out to 83.92 kilometres. And to calculate the area, I took the average of the two widths because it's slightly wider at the bottom and a little bit narrower at the top. Actually it's a trapezium, and I took the average of the two widths and multiplied that by the length to get 18,374. Some of you had like triangles, you had like a rectangle in the middle and two triangles, and you can get there, but it's a bit more complicated to calculate the area in that way. Then you're asked what's the difference between raster and feature classes, and I really set this problem up so that you've got some feature classes here, some points at the corners, and also a raster for the DEM. Actually, strictly speaking, the topographic map is a raster as well. So what I was looking for here was that rasters provide continuous coverage over a geographic space, and many of you mentioned they have grids and they have cells and all that. That's true. Feature classes contains point lines or polygons that are discrete spatial objects that don't cover an entire space. Those are the things that I was looking for. Any additional thoughts, Dr. Tarleton?
No, that was the same we were looking for here.
Mm-hmm. Okay, so question number 2. You're given the coordinates of this particular coordinate system, the projection parameters, and asked to specify some things about it. Firstly, what Earth datum is used, the North American datum of 1983. I think pretty much everyone got that. It's specified here, North American datum of 83. What is the spheroid used? This is GRS 1980, which is the Geodetic Reference System of 1980. That was the first Earth representation that was geocentric, worked out from satellites. And then what map projection is used, and I've got here USA Contiguous Albers Equal Area Conic, because that's the full title of this. Now, quite a few people just put Albers. The Albers projection is used in many circumstances. It's not just used for this particular projection. So when you say what map projection is used, that implies what is all the set of parameters that are associated with it. So it's not just enough to say it's Albers. Albers was a gentleman who did map projections. He did other things and even equal area projections. So I asked for the full title here. And then you're asked what's the show in the diagram below, what were the dimensions of the axes of the spheroid. And most people got the idea that the semi-major axis and semi-minor axis were indicated by the numbers that are given at the bottom of the projection set. Quite a few people had these as diameters and not as radiuses. So that when the term semi-major axis and semi-minor axis refers to the fact that these are like equivalent to radiuses, even though it's for an ellipse. In the next part, you're asked to draw the lines for the central meridian, the two standard parallels, and the latitude of origin. Most people got the lines drawn okay. I really tried hard in the review session to emphasize the idea that the x0, y0 is the false easting and false northing, but still some people didn't do that. I was a little bit disappointed. But anyway, it's 0, 0 here. It's not 96 and 37.5. Those are the phi and lambda values for the the origin point on the original globe. They're not where they're not its x0, y0 coordinates. That's the false easting and false northing. For the decimal degrees, we're doing this in the traditional way, just calculating for decimal degrees for latitude, 38 plus 54 over 60 plus 17 over 3600, and for longitude, you have to have minus here. Decimal degrees implies a sign. It's not enough to say blah, 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 west. It's got to be a negative number here. And then we had the UTM zone of Washington, D.C., which turned out to be a bit of a wild card. In this class, 1/3 of the students got this right. Yeah, 2/3 did not. So anyway, good to have wild cards, I guess occasionally. So these zones are 6 degrees wide. They start at 180 degrees west. So if you take 180, subtract from that 77 degrees west and divide the result by 6, you come to 17.16. That means there are 17 complete zones before you get to Washington, and then a bit more. Yes, AJ?
Can you remind me why it is it starts at 180 and not at 0?
So why is it?
Which way are we rotating?
Okay, so the UTM coordinate system was actually set up by the US military during World War II. So this is, the time when the US had global concerns. So they started at 180 degrees west and went right around the Earth and came back to 180 degrees east. So in other words, the line that is the origin point is actually out in the Pacific Ocean. It passes just to the east of New Zealand, actually. New Zealand is the first country that sees the sun, if you ever worry about that, yeah. So there's 360 degrees of rotation. Divided by 6 is 60, so you've got 60 zones all the way around. And it was just an arbitrary decision that was made at that time to start at 180 degrees west. And I think you can sort of, if you sort of think it out, that they were trying to go right around the Earth. So if you go 180 west round to 180 east, it's kind of like from the beginning to the end. If they'd started at 0, they would have gone 0, which then round to 180 east, and then they would have switched to 180 west and come back to 0. I guess they could have done that. It would have been centered on Britain. This was done by United States, so maybe that's yeah. There we go. There's the answer there. Anyway, honestly, I don't know the reason why it started at 180 west. But yeah, well, you can see quite a lot of people were dividing by 6, and they were starting from 0, and there was a good deal of creative math here. So. Okay, Dr. Tarleton, do you have any additional thoughts?
I guess the only thing I would say with respect to this question was that I was accepting Elba's just by itself for the projection.
Oh, well, you're an easy guy. I'm a tough guy, yeah.
The rationale for that is the semantic that I'm trying to sort of think of is the projection is the sort of method that's used for coming up with distorting the Earth onto a flat plane, whereas the coordinate system is all of the details.
Yeah.
So the coordinate system is the projection and the origin and the parallels and all that.
Okay, so those.
But it's semantics at some level. So yeah.
So at least those who got a point, lost the point here, will know that everyone who did the same got treated the same. So question number 3. The first thing that you were asked to do was to calculate the area of the 2 catchments, which is a fairly straightforward thing. You just add up the component areas of the pieces that are contained within them, when they intersect these precipitation cells, 1.396 square kilometres and 1.479 square kilometres. Then there was a bit of a confusion at this point. So the question was for catchment 1644362, determine the national water model grid cells that it intersects and the fraction of the area overlapping with each of these grid cells. So what we intended was that if you looked at catchment number 1644362, you'll find that it overlaps cells 2 and 4, and indeed if we go back here, you can get the individual areas, which are 122, 1750 and 256, 950 for those overlaps, and if you divide those by the total area, then you get the fractions 0.826 and 0.174, and then if you get the weighted average area weighted precipitation input, you just multiply the two rainfalls by those factors and you get the result. Now, quite a lot of people interpreted the second question, the first question up here, differently, and took the proportion of the area of the catchment within the grid cell. In other words, looked at this piece here as a proportion of the cell area and this piece here as a proportion of this cell area. So because quite a lot of people made the same interpretation, I let it go if you got this one right. So in other words, to get the part C correct, you have to effectively do this calculation anyway. You have to do this 0.826 and 0.174 correct. So if you got this part right, I just let this go, whether you did the intersection with the cell areas or with catchments like what we asked. Any questions, any additional thoughts, Dr. Tarverton?
Well, I guess that I can probably take the blame for having written that B sentence, and I thought it was perfect here, but apparently not.
Yeah.
So I did the same here. If you calculate the proportions of the cells, then I interpreted those being correct, but you had to do part C right to effectively get the answer that was. So yeah, if you use those proportions that didn't add up to 1 in part C, it doesn't make sense.
Yeah, it was 0.304 and 0.06 or something with the proportions. Actually, there was one person who did this and who took those proportions and divided them by the sum of the proportions. And it turns out that actually works. So yeah, there is so if you had like 0.306, which is the proportion of cell number 2 and as a function of this big cell, and 0.06 or something, I forget exactly which one it was for the number 4, and then you divide by the sum of those, you can actually get the correct weighting factors here. But not just multiplying it directly by the factors that you see here. Okay, the last one. This was a skill that we've gone over a number of times. So 13 and 12.5 have to be raised to 13.5, and then you write that in the diagram next door and do the work from that diagram from that point on. The flow directions are given in the diagram below here, and most of them are pretty obvious actually. So in the case of the 13.5 cells, then you can tell that there's basically a channel being created here, so you just go vertically upwards, and I drew this little diagram with the arrowheads on it just so that I remind myself as to what those numbers are, because it's hard to remember them all. And then here from 16, you can go 16 could go to 13.5 on the diagonal or 13.5 on the direct axis, and the direct axis is shorter, so it goes to the left. 16 here, and similarly 15.5 goes to 13.5 on the diagonal or 13.5 on the horizontal axis, so this is 16. 16 cell up in the top right hand corner goes to 15 out of the square here, so that's the 64. And the only one where there was some reason to check was number 16.5, and if it could go to 16 on the axis, which has a slope of 0.05, or it could go to 15.5 on the diagonal, which has a slope of 0.07, and that's the bigger slope. So it goes on the diagonal, which is a slope of 32, and that's determines the flow directions. Most people got that right. The largest slope of any of these drops is from 16 to 13.5. You can sort of look around and almost just determine it by inspection. And that comes to 0.25 as the slope, and it's in the cell in the middle bottom of the grid. And then you're asked to calculate to draw the flow directions, and just to help myself in drawing this diagram, I redrew the little arrows here. So in this case we go, and you don't worry about the cells that are on the outside at all. So this cell goes straight out, so that has no flow accumulation, nothing comes from upstream. This cell goes over here, so it's an origin cell, and this cell goes over there, so that's also an origin cell. This is 0, 0, 0. Then we've got 1 which comes from upstream there, 1 which comes from upstream there, and then we've got 2 cells with each with 1 upstream plus themselves makes 4 here. Or in total you've got 5 cells that form the watershed, and the accumulation at the outlet cell is 1 less than that because you don't count the cell itself, and that means that the watershed is shaped or shaded like this, and the area is 5 times 10 by 10, which is 500 square meters. Many people got that. So Dr. Tarleton, you have any other thoughts?
I think that was generally pretty well done here too. I guess overall in the test as a whole, the only real challenge was the UTM question. And I guess there was another challenge a little bit on the question on where there were the axes of the spheroid. Some people put the diameter rather than the radius.
Yeah.
But otherwise, it was generally well done.
Yeah, and actually I was thinking, while you were going through this, you know a lot more about maps and about coordinate systems now than you knew at the beginning of the semester, right? You see how this whole system is set up now. And I think that's actually important, really basic information. When I first started doing GIS, it was this kind of stuff that I needed to learn because I didn't know anything about this at all. UTM is some number system that they put on the bottom of maps. I mean, I was just completely ignorant about it. Okay, any questions about that?
Maybe there's one more comment.
Yes.
There's also an important thing that I think we're learning is a bit of sense of scale and the sort of numbers we're dealing with. And I guess question 3 brought that out, where the shape areas were in square meters and the question asked for them in square kilometers. And it said that those were 2 kilometer by 2 kilometer boxes. So you should be getting an area number that's sort of on the order of 1 to 2 kilometers, and that should give you a reality check. Some students just added up the numbers in the table and left them in meters, so not multiplying by the 10 to the minus 6, and ended up with thousands or numbers in the millions and wrote down square kilometers. And you should realize if you write down a number in the millions in square kilometers, you're talking about something like the surface of the Earth or the surface of the US rather than the surface of a little box here. So try and think about the numbers and their scale as you write them down.
Mm-hmm. So the area of the continental United States is 8 million square kilometers. The area of Texas is 700,000 square kilometers. You know what the area of Germany is? 350.
200,000.
350,000 square kilometers. Texas is twice as large as Germany. So. Go Horns, yeah.
Yeah?
I was curious what the class average on the test was.
So the question was, what was the class average? Here in Utah, I scored it out of 80. The class average was 70 out of 80.
And here it was 91.8 out of 100. Hmm? Yeah, I sent around an email about that, Perez. Yeah, there's a distribution of grades by ranges in an email that I sent out just before class. Okay, any other questions about that? If you've got questions about the grading on your quiz, please come and chat with me after class. So let's move on a little bit. So today we're beginning after the midterm exam, and we would like to get a project update, term project update. So I've put an assignment on Canvas called Term Project Update, which is the same as the assignment for the term project proposal, except I added a thing here, a base map. Please apply a base map. So the requirements here are just the same as they were before, but I'd like to see a map. And that's due a week from today. So it's Thursday of next week. And if you could also submit your proposal or your update through the HydroShare system, that would be good. Do they have to just follow the same instructions, Dr. Tarleton? Or?
Yes, they follow the same instructions. They just have to name the file that they add differently. So I believe it's called Progress Report. And you should be able to see, there's a page that at least I've set up, and it's got the Texas students as well as the Utah State students. And if you click on the word where it says Project Report, if you've loaded your file, then it should automatically download. You should add it to the same resource that you created before. You don't need to create a new resource. You just go back to the same resource, add a new file to it called Project Report.
Is that?
So if you...
Which one
is that? Yeah, so wait, go to look at, go further higher, go higher up. There's a students.html, just slide up a little bit more.
Okay, there we are.
There.
Okay.
So I figured out a script to automatically generate this file. So if you hover over one of the things that says proposal, you'll see it gives a link to the proposal.pdf in your HydroShare resource. If you hover over the interim progress report, you'll see, okay, so now you're going to download that student's proposal. If you hover over interim progress report, you see the file that you have to add has to be interim progress report. Since it hasn't been added, it'll give an error until that student adds that.
Yeah. Okay. Any questions about that?
And so I guess I differed a little bit. We initially said that the due date was the 23rd, and that's what it still says here, so I'll have to rerun this to update that. You pushed it back to the 25th. Here I thought that since we were maybe lagging a little bit behind, I made it the following week. So at least here the deadline is I believe it's the 30th. You're welcome to do it early if you want to, but the 30th is the sort of last day to do that.
Okay. Well, we're the 25th.
So
We're good. Yeah, we're good. Yeah, there's another assignment that's due on the 25th. So you're going to get it on the 25th, so that's why I put it on the 25th. Anyway, it doesn't really matter. I just wanted to basically just make a map and show where you're working, and that's the thing that I want to. And also just to stimulate you to start to change gears now. You're getting off of getting assignments, and now you're getting to the point where you're supposed to be doing creative work yourself. Any other thoughts, Dr. Tarberton?
There may be well, I guess I had prepared right at the beginning of the semester a set of guidance on what the interim progress report should be. I'm recording it right now. I'm not sure how consistent that is with what you just said. So,
well, why don't we just,
I guess if you, but anyway, so I guess go and look at the web page you're looking at where it says interim progress reports due under the term project. Go lower down. There. That one. I mentioned what that says. So that's at least what I was asking the Utah State students to look at. So I think it's the same, but a base map adding that would be great. And I'm actually going to be asking each of you to review two of the other students' progress report in the class and give feedback as well as me. And the questions that you'll have to answer are these ones down below there. So we're going to do a little bit of sort of peer work here.
Okay, thank you. Anything else? Okay, let's move on then. So we are having a situation here in Austin, which you may be aware of if you follow the news media. So we have above us a Highland Lake reservoir system. The big dam is at Mansfield Dam at Lake Travis, and above that there are 6 dams called the Highland Lakes, and above that is the Colorado River and some tributaries, the San Saba River, the Llano River, and the Pedernales River. So yes, well, on Tuesday we were having our exam. That happened. So on the Llano River at Kingsland, this bridge doesn't exist anymore. And this is actually kind of interesting. So let's see if we can. Okay, so I think there's an ad here first for something, so ignore the ad.
You're supposed to go and buy the product.
Yeah, well, good. I'm glad. So we don't have to listen to any sound. Yeah.
Whatever it is.
Yeah. Okay. So this is now.
Oh my God! Excelsior, the bridge collapsed. Excelsior, the bridge collapsed. The Excelsior.
You can see that this part wasn't planned out.
Oh, is that? Oh my God! Excelsior, the bridge collapsed. Excelsior, the bridge collapsed. The Excelsior. Oh, get back, get back, get back. Yeah. Yeah, Chris, we're okay right now. A lot of people...
And there are pieces of
Chris,
the
we're okay. A lot of people right now running back because some of that water did rush up a little further on shore here. The bridge collapsed just in the past minute or so. We heard a very loud sort of rumbling noise, and everybody had their eyes on that bridge already. It is completely collapsed there in that middle part where most of that water was going over. Now you can't even tell that there was a bridge there at all. And so when it did collapse, you can see, look at these, wow, look at that out there, that wave. Because of the force of that bridge and all that concrete now coming down the river, it's really impacting how high this water is getting on shore. So a lot of people, I'm sorry. Oh, I'm sorry. We're seeing pieces of the bridge out here flipping. Leslie, if you can get a shot of that, the pieces of the bridge just flipping over.
Okay, well, there we are.
Oh, I'm not ready for this. That's Jake's worry monster. I was thrilled when he had his health scare, but now he runs and drinks palm.
Oh, looks like an interesting guy. Yeah. Getting ready for Halloween. Okay, so we are working with the Texas Department of Transportation on a bridge portal to look at the conditions of flow at about 27,000 bridges in the state. These blue dots are where the USGS gauges are in Texas, and the green and blue area that you see here is the rain as it existed on Tuesday afternoon. So after we had the quiz, I went and screen captured a few things. And the bridge collapsed on the Llano River. And so this is the most upstream gauge on the Llano River, and this is the water level that is being calculated by the National Water Model and what is also being observed. So the vertical axis here is in feet, and the solid line is the observations by the US Geological Survey at this location, and the dashed line is the forecast coming from the National Water Model converted to the water levels using the hand method that we're going to learn in class next week. And that's at Junction. This is the Llano River near Mason. At Junction, you can see the level here is about 27 feet, so the water's 27 feet deep by that point. When it gets downstream to Mason, now the level is over 30 feet, 33 feet here. So it's already 6 feet deeper when it got to Mason. And then you can see again, this is the forecast coming from the National Water Model, and this is the observation. So it's actually two peaks in the hydrograph at that location. And this is the Llano River at Llano, which is further downstream again. And you can see there's a fairly good relationship here. By this point, the level is 40 feet. So the water is 40 feet deep, and it was then downstream of there that the bridge went away. So at that point, you've got an event sufficient to wipe out a whole highway bridge. And this is not an interstate, but it's a big bridge. This is not a small country road here. So this is the flow, a diagram on the left, which shows the discharge on the Llano River for the last week. And the blue line is the observed discharge calculated by the US Geological Survey. And I looked up the table and found that little peak at the top there, it's a log scale, so it's not easy to see, but it's 276,000 cubic feet per second. Now that's a serious amount of water. And the red asterisks there are times when the US Geological Survey has done flow gauging at the river to check the gauging is correct. There's also records kept of the annual maximum flow, which is the largest flow at any instant in a year. And you can see here the starts in the 1940s, and there's one dot in 1936, which is way above 276,000 cubic feet per second, but all the others are below. This is the yes, AJ.
Is that before the dams?
That's a good 1936. So this was, yes, it was. It was just before when these dams were built, right? So these dams were built really, well, really to do what they're doing right now, right? To absorb this big flows of water. You can see there's a big flow here. So Texas was in a huge drought in 1952. So there was dry weather for 4 years, and all of a sudden, on one day, September the 10th, 1952, an enormous flood happened. Lake Travis filled up like 60 feet in one day. And so the boats just went glug, 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 and they went down. And an incredible event. And then the drought went on for another 4 or 6 years. And that was that point there. So this is an historic event that's happened on the Llano River in the last couple of days. However, the water doesn't stop there. It keeps going. So this is a somewhat relevant situation for us who live in Austin. So since this is October the 15th, and here we are October the 18th, so Lake Travis has risen by 34 feet in the last 2 days. And the spillway is at elevation 714. So there's 12 feet to go. Now you can see that in the last day or so, the rate of rise has flattened off, but it's still rising. And it's anticipated that tomorrow the level will be something, or over the weekend, that will be something of the order of 710 feet above mean sea level. So the margin for error here is not very great. The Lower Colorado River Authority is opening floodgates to try to let water out, and so you can see there's only been a little bit of water let out up until this point. That's when they generate power, actually. But now they're opening the floodgates, and so this is the discharge that's coming out of Lake Travis, about 27,500 cubic feet per second as of this morning. Now, this is what the dam looks like. This is Mansfield Dam, which is on Lake Travis, and you can see water coming out the floodgate there. There are currently 4 of these floodgates open. Now you can see that there's quite a lot. I think there's actually 24 in total right across the dam there. Once they start opening a lot of floodgates, then the water level starts rising in all the lakes that are downstream of the dam. And with 4, it's okay. It's not going to get anybody flooded. But if more water, if they start opening more gates, then the whole thing rises and more close to the stream properties get threatened. But the big issue isn't really the floodgates, because they're sort of controlled. It's the spillway. See, there's the spillway. There's no gates up there. So once the water gets to 714, it just goes straight over the top. What goes in goes out. So that's a serious circumstance here for Austin. This is kind of a situation that doesn't happen very often, actually. So I checked the forecast. Well, here's Lake Travis, and this is the Mansfield Dam, which is the bottom end of Lake Travis. So all this area below Mansfield Dam is the area of concern. The purple colors that you see here are where the National Water Model picks things up again. It doesn't do forecasting on lakes because of this thing. That the amount of water that's coming out of the lake is actually not physical at all. It depends on how much the Lower Colorado River Authority decides to let go. So they can't forecast that. It's a human decision as to what the water is actually going to be in here. But we're down here in the city itself, and then I checked the medium range forecast here from the National Water Model. Yeeks. A little bit of a blip here. So about a week from today, there's anticipated to be another storm passing through the area. So this is one of these to be continued stories. There's never been a flow over the spillway of Lake Travis since it was built in the 1940s. But yeah, we don't know what's going to happen next week. Okay, so that's well, Dr. Turreton, you have any thoughts? Any questions?
No, except that well, maybe I'll go and see if I can change the exercise from Onion Creek to Llano River for the hand. We'll see how hard that is. If it's not too hard, I'll switch the exercise and we can actually work with that stream reach. I guess you'll find out next Thursday whether I've been able to do that or not.
Okay. But I think you can see the relevance of the work and the research that we've been doing here over the last several years. Huh? I mean, there's a bridge just gone. You know, we're working with our Department of Transportation, and actually as this goes along, we're learning about how to optimize the portal that we've made for them. One of the things that we found is that the USGS has a stage height at each gauge, but sometimes the stage heights, for example, there can be almost no flow and the stage height is 10 feet. And that's because they put the datum of the stage well below the bed of the river in case the bed of the river gets eroded. But it means that, you know, calculating water levels and comparing them to observed stage heights can be just gobbledygook. And so what we're doing is we're actually adjusting this so that the stage heights and water levels are consistent with each other at each gauge. And yeah, this is a learning experience, but I think it's possible that we will be able to, in the bridge portal, start making some red dots like, this bridge could be overtopped. I mean, the bridge that went out was not overtopped by much. You could still see the guardrail, so the water was just flowing over the road. It wasn't very deep at all. And so basically the force of the river on the bridge deck itself was enough to take the bridge out. And so, you know, clearly those are public safety concerns that we would want to have some capacity to anticipate. Okay, so how can we do that? So I talked last time about Hurricane Harvey and about how flood forecasting is done, and I want to pick up from the lecture that I was giving, and I stopped a week ago, and talk a little bit about the Texas flood response system and how can we do better. So after we built the prototype of the National Water Model, then the question became, how do we anticipate the kind of situations that we're just looking at here and be able to understand, you know, what will the water actually spread out like? It's not just how much flow is there, but how deep is it and how wide is the water? And the National Weather Service has maps like this at about 34 locations in Texas and at about 130 locations across the country. This one happens to be on Onion Creek at Highway 183. There's two elevation axes here. One of them is the larger numbers on the left means the height above geodetic datum of the water at the gauge, and the one on the right is the stage height, which is the height above the arbitrary datum that's established at that gauge for measuring the depth of water. And as the water level gets deeper, the water spreads out, and this is a distance of about 10 miles. So for 5 miles upstream and downstream of this one dot, there's some intelligence. The only problem is there's almost nobody lives here. Lots of people live on Onion Creek. It's actually been a very flooded area, but not too many in this reach. So the place where the gauge is and where the mapping is isn't really where the public safety risk is on Onion Creek. However, when I looked at the data, I asked for the data for all these maps, and what I saw was actually a combination of rasters and vectors. I saw a polygon, which was the outline of the edge of the water, and a grid, which was the depth of the water underneath the surface. And it was just indexed by 1 foot interval. So there's just a big stack of polygons, a big stack of grids. And I thought, oh, okay, well, why don't do that? Why can't we do that for the whole country? Another thing that's available at the gauge is a rating curve, which relates the water level to the discharge. So when the water level is measured, which is what's going on all the time, the discharge is inferred, and this curve is built up by stream gauging. In other words, people go out there and they just physically measure how much the discharge is with meters, and then they know what the water level is at that time, and they build up this curve, which is an empirical curve derived at each gauge individually. So we've got these two things. We've got maps and we've got rating curves, and so the question became, how could we do this across the country? And then Dr. Tarberton stepped in. So Dr. Tarberton, do you want to outline your inspiration about this map, how to do this?
Well, I don't think I can claim all the credit for that. But so the general idea is that from a digital elevation model, you can get the height above the stream. And I think as I recall the story, we were at a meeting in Tuscaloosa, and Dr. Maidman came to me and said, you're a digital elevation model raster type person. Is there any way that we can calculate the height any point on the terrain is above the stream from the sort of tools that you've worked with. And I sort of said, well, yeah, there actually is a TOWDEM tool that does it. It's called distance to the stream, and you can calculate it in the vertical sense. So then we started effectively trying that out, and that led to the approach that for every grid cell you effectively trace down, and it's part of the D-Infinity tool set. So you trace down looking, averaging across the multiple flow directions that D-Infinity gives you till you hit a stream, and you effectively back from that and get the average height that each point is above the stream. So that's the sort of first part of the method, and that allows you to tell if you've got the depth of water in the stream, how where it's going to flood. And then there's a sort of second part to the story that came, that you can actually start then building up the volume of water over a reach given that depth, and with volumes and lengths you can get average cross-sectional areas, and you can start getting hydraulic properties. And that was effectively figured out and published in papers that came out, I guess just this year, man. It might have, the first drafts of them came out last year and the years before.
So another thing that we did besides working with Dr. Tarberton was to collect together the address points of our state. So every building where you can ask for an emergency response vehicle to come has a point. This building has a point. So if we call for an emergency here, the dispatcher sees a dot. It just says, go there. And there are 355,000 of these in Travis County. There's 9.2 million for the state, and these are compiled by the emergency communications districts, which are maintained within the cities and counties. So we at UT Austin went around all these districts, and there's a lot of them, and we vacuumed these data up for all of Texas. And now the Texas Natural Resource Information System is going to maintain this as a statewide data set, so that we can look at the impact of emergencies and find out, how many people or how many buildings are going to be impacted. So this is the height above nearest drainage idea, which Dr. Tarberton mentioned. It's just to say, if I'm at a certain address and I'm this high above the bottom of the stream, then if the water's height is less than that, then I'm okay, and if it's greater, it's not okay. And we worked out this map, the hand map for the continental US, using a supercomputer system at the University of Illinois called Roger. And one of the ideas that I had was that I imagined that this stream is like a tube. Just in my mind, I saw this as a tube. And actually, this goes a long ways back when I co-authored a hydrology book when I was much younger than I am now. And in that, we did a calculation which showed the equilibrium of gravity and friction. And when you have equilibrium of gravity and friction, then you've got a uniform flow system established in the channel. And so for a certain depth, we can say, well, if we've got a digital elevation model, we can measure the surface area, and we can also measure the wetted bed area, because we can take the angle on the slope. And if we have the surface area and we know what the increments of height are, we can calculate what the volume is. So for this channel, then we can calculate the volume, the surface area, and the bed area. And if we divide those by the length, the volume over the length gives the cross-sectional area, the bed area over the length gives the wetted perimeter, and the surface area over the length gives the top width. The ratio of the area to the wetted perimeter gives the hydraulic radius. Those are the things that you need to do hydraulic calculations. So what we're doing then is, instead of doing things by cross-sections, which is what's traditional done in hydraulic engineering, we're saying this is a model for the whole channel reach. And so what we did then was to take the NHD Plus data set and the digital elevation model, and with a series of scripts that were built from TOWDEM and other related functions, we developed a sequence that which overlapped the catchments and flow lines with the elevation model. And then we had two rasters created, one for the elevation surface, which is the elevation from geodetic datum to the bottom of the channel, and then one from the bottom of the channel up to some level, which is the blue here. So for Bernoulli's equation, z plus y plus v squared over 2g, so we've got the z term and the y term here. And with that, we were able to say, okay, here's the height above nearest drainage map. And if we say, okay, if the height above nearest drainage is 15, what do I get? And then you get an inundation map, as you see here. And we can do that for every increment of distance. And so we did that in 1 foot increments for the whole continental US, 3 million miles of streams and rivers. And here's an example. This is a stream that I used to be the drainage engineer for a long time ago. City of Rollingwood on the southwest side of Austin. I only worried about one creek. It was called Dry Creek, and now it's called Eanes Creek. But hey, they got a little more professional over the years. And it's just one creek. It goes down through the city. It's about 4 miles long. It has a drainage area of 3 square miles. And if you go through and do these calculations, then you have the hydraulic radius as a function of the depth, the cross-sectional area as a function of the depth, and you can estimate the bed slope from the digital elevation model, and from that you can derive a rating curve, and then we've got a little rating curve that applies to that particular stream reach. Actually, it applies at the outlet of that stream reach, is the truth of the matter, because that's where the full drainage area applies. And so from that, if we have the forecast from the National Water Model, we can calculate the flood depth and we can estimate it. And so we built a system that did that, and that has now been implemented at the National Water Centre. So they have taken on, they've recalculated the same process for the whole country, and they have tested whether they can do this fast enough to do the inundation mapping while the forecasting is going on during flood events. Because in these kind of things, it's not enough to be able to do something. You have to be able to do it in 2 minutes maximum, 3 minutes. I mean, you can't, time really matters. Since these forecasts are being renewed every hour, and you've got to do a lot of other things before you get to this point, you haven't got much time left to do this part. And they proved that they could do that, actually. So that then forms the Texas flood response system. So we take the discharge from the National Water Model, we transform the discharge to the depth using the rating curve, we convert the depth to inundation using the inundation map, using the hand method that you'll hear more about next week, and then we assess the impact on people on property using the address points. And so this conversion here from discharge to depth is what I was showing you on the Llano River, you know, the real-time result on the Llano River. So this is what happened during Harvey. So Harvey came ashore on Friday the 25th of August, and at 3 o'clock in the afternoon I made this calculation that showed that Region 2, which is southeast Texas, was due to get 238,000 address points flooded. And Region 6 was 22,000. And Region 1, which is over to the south here, was 3,000. And, sorry, up by Dallas is about 3,000. Now, I didn't know if these numbers were right, but what I could see was that there was an enormous difference between one region and another. So it wasn't the absolute value that mattered as much as like the huge difference here. So it was just clear, Houston is going to get creamed here. Now, this was before the hurricane got to the coast, and it made landfall down here in Corpus Christi. The Houston is 165 miles to the northeast. So that shows that it was possible to know that Houston was going to get creamed before the hurricane even got to the coast. So then what actually happened? So the Texas Division of Emergency Management collects records of buildings for which public assistance has been requested for their repair. And they've got a total of 152,800 buildings. And at the time that the hurricane was coming ashore, I predicted that the top 5 counties that would be impacted were Harris, Fort Bend, Brazoria, Galveston, and Montgomery. That's, you know, they're all here in the Houston area. And what actually happened was Harris, Orange, Fort Bend, Montgomery, and Jefferson. And Jefferson and Orange counties are right here in the east part of Texas, and they got creamed in the deluge that happened in Beaumont, Port Arthur, right at the end of the hurricane, which wasn't anticipated. So, but you can see that we were able to call the impacted counties pretty correctly. This is the proportion of the total damage that actually happened compared with what was forecast to happen. So the orange here is the proportion of the total number of buildings that were flooded in each region, and the blue is what was forecast. And you can see that they're nearly the same. There's a bit more damage here, the orange in Region 3, which is here, and that's because this is a hurricane that's got wind damage as well. It's not just flood. So this model is just about flooding. So we didn't catch that part. Actually, I had a condo down in Port A, which is, we just got a shell left now, actually. Oh, we got. So the end result of this assessment then was that it was possible to understand what the impact of Harvey was going to be before it got to the coast. And you could actually, now I don't think anybody knew that actually. This is a kind of a first thing. And it's only one data point. I think you have to do this a few times before you get confidence that you've got a better result. Now, we were just looking at a bridge that broke a couple of days ago. There are 27,000 bridges. Texas has 27,000 bridges on 15,700 stream reaches forecast by the National Water Model. So if you want to say, look, now we're calculating all these flows everywhere, we better be measuring them at more places than we are at this point if we're going to be able to really have a reliable system. And so the beauty of the National Water Model is it enables the whole system to be thought of as a system. Like this is not just a forecast of one bridge or one something like that. This is a forecast of the entire state. And so we've built this portal that I showed, and we've also started working with the Texas Department of Transportation to measure the velocity and level of the water using radar measurement technologies. These come from a company called SOMA, which is based in Austria. And so we're starting to figure out how we could install these on bridges and do some additional work there. And so this is a setup that was prototyped at the National Water Center in 2016 during the Summer Institute. This is an instrument called an RQ30. And so what it does is that it measures the elevation down to the water. So one beam goes straight down, and another one goes out onto the surface of the water, and when there are little ripples on the surface, there's a kind of a Doppler effect, and it bounces back, and it can measure the velocity on that point on the surface with this Doppler effect. And then in the river itself, if you use an acoustic Doppler current profiler, that's another system that uses the Doppler effect, and they take a boat across the river, and from that they get the velocity profile right throughout the cross-section and not just at one point. And if you take the ratio between the velocity on the surface and the average velocity across the cross-section, then you can estimate the discharge. And you can see the blue line here is the difference of the actual velocity measurements, and the red line is what they estimate the actual velocity to be. And the departures between the blue and the red are weird because of wind. So if the wind blows, you got sort of, it's less, it's more, it can sort of muddy the situation up here, but if you take a sort of average through the middle of it, then you get rid of that. So these instruments come from a company, Hydrological Services America, and we're starting to implement them. Now, if we're going to really get this tied down tight, we need to be able to do some measurements in the water itself. So this is a gentleman by the name of John Sloat, and he's from a company called WaterCube, and he went on the Cahaba River and he had a canoe and he paddled around, and he's got a acoustic Doppler current profile at the bottom behind there, and he was able in just a few hours calculation or measurement, he got 50,000 points on this river. It was amazing, incredible coverage. He went up and down the river and he got beaucoup data. Just a couple of weeks ago, I went out to the Colorado River and I saw another thing which was like a remote control boat. And so the Lower Colorado River Authority has a remote control boat. They don't even need the canoe. They can just dial it up and drive this boat around. So it's really cool. So we need this kind of information that will be telling us what's going on underneath the water surface, because the LiDAR data doesn't penetrate water. What else do you think we can use at these bridges to tell what's going on? What's the latest in photogrammetric technology that's being used? What did you hear after? I'm sorry? No. Taking images from where? From what? Drones, yeah, drones. So what's becoming a standard now is drones and using drone technology. So if you imagine now, and so TxDOT actually has a photogrammetry section, and so we're going to ask them, can they then do the equivalent of this, but with a drone flying above the surface so that they can measure all the physical structure of the bridge and all what else is going on around this. So by combining these two things, you get a complete representation of the terrain upstream and downstream of the bridge. So that'll be a sort of a new twist to see if we can get TxDOT to do that. These are some of the data that come from the bathymetry and velocity measurements. So this is really cool. Right along what you're seeing on the left-hand side is the bottom of the river. This is over a distance of about 300-400 yards, something like that. It's just upstream and downstream of the bridge. and the threads that you see here are the measurement of the velocity. So this is, you can see, it's kind of a complicated situation in this river that, it goes in and out, and there's threads and twists and turns and all that. But the intent, so the idea is that if we can measure the velocity here, or more particularly, what else do we want to do besides just doing these measurements? What should we be doing? Inspirations. We've got lots of bright people here. Dr. Tarverton, you have any thoughts?
Well, we should be trying to model it, compare it to what we're getting out of models. Think about perhaps the approximations that went into the hand equation, which we saw really briefly, things like Manning's N, things like assumption of uniform flow, differs a little bit from the reality. So you might consider applying a high-resolution hydrologic model and see where you can improve over the simplified approach.
Yes, so this is sort of almost the reverse of the National Water Model. So instead of thinking about an approximate approach that you can use anywhere in the country, how do we just turn yourself on your head and say, how do we really get something good at the location of one bridge and just nail this, get it really right? And so yes, we want to be able to do hydrodynamic modeling of these flow patterns so that if we measure the level and the surface velocity, we can then extrapolate from a hydrodynamic model what actually the flow patterns look like and what the flow is at conditions other than what they were measured at. So instead of having to go out there with field parties every few weeks and do measurements of the rivers, as is traditionally done, we can actually construct the rating curve using a detailed hydraulic model. And that's what we're going to try to do. And so we're going to do this at 20 locations. This is the brown line here is Interstate Highway 10. And the east side here is the Louisiana border, and this little kink here is in San Antonio. So this goes roughly from west of San Antonio to the Louisiana border. And we're, at this point, just choosing and scouting out the locations for these sensors, and we're going to put them on the road. And one of the things that's actually interesting is that in these areas down here in East Texas, the river is actually in a tidal zone. So the water goes both ways. The velocity can be this way, but it can also be that way. Oops, yeah, that's kind of a complication. That's where you really need models. But now you can imagine that this is kind of like a picket line. I mean, it's sort of like, airplanes flying across the country or something. You need to look up and see where they are. The highway system can be thought of as a sampling system, like a transit, actually. And if you start to think about that, you can say, gosh, if we had this highway, we could measure what's the degree of correlation between the flows and the streams at different locations along the highway. And you could think about what's the stress on this highway, how much water is flowing under the highway for how many cubic feet per second per mile or something. So you can think about what's the degree of risk that's associated with sections of this highway. Because once I-10 goes under, it's our major transportation system. It only has to go over one place, and that's it. We're out. The trucks stop. Transportation stops. And it has gone under several times in the last few years. And if you think about the interstate system, you've got the east-west interstates, you've got the north-south interstates. Hey, that's a national system. You've got a sampling platform for the whole country. So if TxDOT can get this going and we can demonstrate that this works, perhaps that inspires other departments of transportation in other parts of the country to do likewise. So we're not just sort of putting gauges at the outlets of watersheds. So this is specifically designed to think about how to do this on the bridge system. We can also think about, let's imagine that the highway was moved. Maybe it's moved 20 kilometres downstream. So what's the correlation between the flows at the location where it really is and the flows at the location where it would be if it were moved 20 kilometres downstream? And then that tells you something about what's the degree of influence or the predictability of a measurement that's made at this location for the areas downstream. Is there even some possibility of being able to say something about what's upstream? We don't know right now, but you could sort of go through some thought experiments here and move this highway around and think about where it intersects the National Water Model, and then what's the correlation between what's modelled there and what's modelled here, and you've got a sense of spatial correlation about how predictable things are in distance and also laterally to the highway itself. So I think this is an interesting scientific metaphor. Actually, Leah Huling is the research assistant who's working on this. She's not feeling too well today, so she's not here, but that's the thing that we're going to work on next year. Now, another piece of this is called the Internet of Water. So there's a language called the water markup language, and this is what it looks like. So this is the Colorado River at Austin, actually. So continuously, instead of just looking at web pages, machines talk to machines. And for water, they use this language, the water markup language. So here, 208-208-09-14, that means the 14th of September this year. 10:50:00, that means 10:50 in the morning. Minus 5:05:00, that means 5 hours before Greenwich Mean Time. So that's called universal time coordinates. The discharge was 136 cubic feet per second. So the USGS has mounted this water data services for all their gauges across the whole country, and it runs all the time. So you don't, so machines don't have to go to web pages to figure things out. Machines just talk to machines and figure things out. And so we started the research here. Actually, Dr. Tarleton was involved in this in 2004, and then in 2008 we engaged the Open Geospatial Consortium, which is a group of about 500 companies and agencies worldwide, and the World Meteorological Organization, which establishes data transfer standards for the world, in building an international system which was approved in 2012 by the Open Geospatial Consortium called WaterML2, which is what I just showed there, and the World Meteorological Organization adopted that as an international standard for water resources time series for the whole Earth in 2016. So this is now the international standard for the transmission of water data. So, for example, I've got the loop here at the bottom, so if we just click at the bottom, we can say, yes, I want to do that. And there is the flow. So if we say, gosh, I want to know the current flow of the Colorado River at Austin, 28,300, 28,300, 28,300, 28,200. This is what's coming out of Mansfield Dam, actually. And so this is the current value, so 2018, 10, 18, 1245. So yeah, that was, where are we now? We're at about 125 here. So there's a latency of a little bit less than an hour of that information. And that's a national, it's a national system nationally combined. So this is happening all over the country. So now let's imagine that this is not just a system for one organisation uses. So what's happened in New Zealand, my native country, is that water data is collected at a number of different regional organisations, 16 of them actually, and there's one national organisation called NIWA, and they have integrated them all with the WaterML language, and so they've achieved a national synthesis of their data without centralising all the information. So it looks like one big system, but it really isn't. It's kind of like the Internet of Water. So that's been accomplished. It's not like we can't do this. It has already been done. And so let's imagine what that might look like here in Austin. So the city of Austin has its own flood alert network. It has 44 locations that are shown by these red dots where they measure the water level. The city itself, for its own flood alert purposes, has nothing to do with the National Water Model, and none of this information reaches the national system. The Lower Colorado River Authority has its own gauging system, mainly on the big rivers and their tributaries. And the US Geological Survey has more gauges, and some that are shared with these other organisations that are purple here. So let's imagine now that there's a system, an Internet of Water, and all of that just looks the same. It doesn't matter if it's the City of Austin or the Lower Colorado River Authority or it's the US Geological Survey or whatever. And so what I think we should be doing is to imagine that we've got a 3-tier flood alert system. At the top is the US Geological Survey. They measure everything, and they're expensive. This is lots of money. At the lowest level, there are water level sensors and local flood alert systems that lots of local organisations develop. The City of Austin's got one, Hayes County has one, and so on. And in the middle, what's emerging is this radar sensors on the bridge thing, which provides more information than what local flood alert systems does because it measures velocity as well as water level. And let's imagine that all of this is now connected together with the WaterML data services, so we've got a statewide flood alert system. And this is what I think we should be aiming at, is a statewide flood alert system that combines everything with the National Water Model. So there we are. So that's my story about what we're trying to do with, sort of thinking, now that we have a National Water Model, how do we support that with linking together the observation systems that we already have and then densifying the measurement at locations like on the highway system for places that we don't measure now. Okay, there we are. Dr. Tarleton, any thoughts?
So maybe I think that perhaps the take-home message from this might be that as one thinks about the sort of data systems that we're scratching the surface with in GIS, you learn the sort of importance of sort of database fields, keys, the sort of organization of the data into a way that different people can work with it and exchange information. And it's really building together lots of systems that can adopt common standards, that can communicate with each other. That's the sort of connected network that's coming along. There's quite a lot of examples of that in things we work with. I mean, the cell phones and the sharing of text messages and various web apps that you have on cell phones is one, but here we're seeing it in terms of hydrologic data, and you probably see it in terms of other civil infrastructure data as well, transportation systems, and perhaps other systems.
Okay, any other thoughts, questions, comments? Yes. Yeah.
National water model, what are the inputs that you have to provide to get the...
Well, it is an adjunct to the weather forecasting system. So it uses the outputs of weather forecasting, which are the rainfall, predicted rainfall, and predicted climate conditions. Those are the inputs. And then the water goes onto the land. There's a land atmosphere model that does surface water balancing and soil water balancing, which produces runoff, and then all the water's geographically transformed using the squares to catchments transform, like what we did in the Thiessen Polygon exercise, and then it's routed down the rivers. So it's precipitation and climate or precipitation and weather are the real inputs. And actually that's where there's a vulnerability. You know, I showed you a prediction there for what will happen a week from today. Right now, that's a weather forecast. I mean, it's based completely on a weather forecast. So we're making a forecast on a forecast. So we're forecasting a flow based on a forecast of weather. So everything depends on the validity of the weather forecast. And those can change. I mean, clearly they can. Yeah. Yes?
Is there a large water model, like a national water model for water quality?
No, there is not. So there's aspirations to do national water model for water quality, but that hasn't worked out yet. But one of the things that would help a national water model for water quality is the geometrical information about volume and area and depth and so on in the river system, because water quality depends on the lag time, or how long does the water spend in a particular reach. And so if we can start to quantify that better with the channel geometries, then our capacity to do water quality modeling is going to be significantly improved. Any other thoughts or questions? Well, just
Any questions here?
Yeah.
Nobody.
Yeah, just
So I would say one thing. There's a lot of uncertainties in this. Some of them we've mentioned. There's a lot of information that is being gathered as we observe things like the big flood in the Llano River. I think there's information in these floods that can tell us about the uncertainties. If we are, for example, getting a calculation from hand that's different than what's actually flowing in the river, that tells us something that either we've got Manning's equation wrong or we don't have the hydraulics quite right. We need to be thinking about ways to assimilate that information back into the models to effectively learn better what the sort of real on the ground behavior is. And I mean, I think that's a challenge that's out there, and there's a lot of opportunities for research and improvement that people should think about.
Okay, so just as a follow-on to Dr. Harberton's suggestion, so I have a colleague, Harry Evans. He was the Chief of Staff of the Austin Fire Department until recently, and now he's been working with us on flood response. And we've got an application pinned to flood map. So he's running around now down by the Colorado River, and he's standing by where the water is, and he's recording where the water is now. So we've got this flow, 28,300 CFS, is passing straight through that system. It's like a constant discharge. And so he's literally doing what Dr. Harberton suggests. He's going there, he's his camera. He's taking a picture and he's recording the latitude and longitude of the point where he's standing, where the edge of the water is for what the flow is now. And so we're going to test out this application, pin the flood map, while the flood is going on in these few days, and then see if we can validate the hand modelling or invalidate it if necessary. I mean, if we're wrong, we should know that. But what I hope we can do is to use the observations of what the current condition is to correct whatever we would have calculated for that, so that if the flow goes higher, if there's more water released, then we'll have a better picture of what actually that is going to look like. Okay, there we are. So this is kind of research and education in real time, you could say. Well, we'll look forward to seeing you next week. Thank you.
Okay, so
Addressing the water issue next year.